Alright, haven't done a forces problem in a long time. Let's do the second one, dynamics number 2. If you look at the scenario, there's a pulley, there's student B, I guess they're hanging off the pulley, and they are 60 kilograms. Student A is standing on the floor, and he's holding the rope, and he is 70 kilograms. So basically, he weighs more than he does. So him just standing there is going to hold him up in the air. And we're told that the rope has negligible mass, the pulley is frictionless, and all that good stuff. And right now they're just suspended. We're asked to do free body diagrams for this scenario. Now, there are 2 different people here, and you got to keep things consistent here. That means you got to draw them to scale. If you're using a ruler, that's pretty easy to do. So just identifying forces right now, the weight of the person, you can write FGB, or you could write mass of person B times G. You can even write out the actual Newton value if you wanted to. So it'd be 60 times 9.81. You could write 588.6 newtons down if you wanted to. And that would probably suffice. But, when you write out the gravity, it tells them that you kind of know what you're talking about here. I'm going to make my tension vector just as large as this. Now, some people write F sub t as well. That's fine. You can write force of rope on person. It's really up to you. It's just as long as you're telling something that's true. But key point here is if we're drawing it to scale, these 2 things should be equal right now because he's not moving. And now, that being said, there's the same rope over there, so it should have the same tension. These 2 vectors should match as well. And then this person's heavier, so what we need is that to be displayed here. And in fact, if you're doing a ruler, you have the ratios of the person. You might make this thing, let's say 3 centimeters, and you can make this 3.5 centimeters, and then they'd be drawn to scale perfectly to each other. If they give you a grid, even easier to do. So this is MA times G. Again, you can write the Newton value if you want. You can write force of gravity times or just force of gravity on person A. You can even write force of earth on person A as well. It's up to you. And then there's one other thing here. This person is in contact with the ground, and so there's a normal force acting on him. And right now I got this force greater than that force. So if this were true, this would be accelerating down till we balance everything out with this normal force. You could call it force of floor on person A as well. It's entirely up to you. Just as long as you say something that makes physical sense here. And that's what my 2 free body diagrams should look like. So, I'm not looking at the rubric right now, but if I were giving you this problem on a test, you got 1, 2, 3, 4, 5 points. You got to identify 5 vectors there. And then in addition to that, labeling them, making sure they're all to scale relative to each other. All of these things matter. And I definitely stress that during your forces test. If we were asked to calculate the magnitude of the force of the floor exerted on person A in this scenario here. So right now, I already calculated this to be 588.6 newtons. That would mean that the tension is also 588.6. And since the tension is the same over here, it's also 588.6 newtons. And then this person here would be 70 times 9.81. So that ends up being 686.7 newtons. And the net force acting on person A is 0. So if we did sigma F equals 0, because all forces are balanced on this person, N is up, T is up, and then it's supposed to be a minus sign right there. Gravity is down. Right? In my mind, there's your expression, your second law expression that's going to get you some credit there. Once you put in the numbers, you'll get your answer. So you have N plus 588.6 minus 686.7. So if we do the math here, It's really just the difference between these two numbers, and I get that the normal force should equal 98.1 newtons. So there's our answer. Now, I think everyone should be able to do that, no problem. You're going to find that usually, it's not always the case, but usually the first couple questions, the first couple parts are easier than the second part. They say that in a new scenario now, this person climbs up the rope and he's actually accelerating. So he's doing it faster and faster and faster with respect to the floor. We're asked to calculate the tension in the rope while he's doing that. And then we're actually asked to determine, does that act pull him up in the air? Because what you're going to find is that the only way for this person to climb up the rope is for tension to increase. And then if the tension increases, it might increase enough to actually get him off the ground. So there is a way for him to get him off the ground. All he's got to do is accelerate up the rope fast enough. Probably not an easy thing to do, but we'll go through the math and see if it makes sense here. So person B is still going to have the same two forces acting on him. There's tension up, and then there's gravity down. That's person B, not A. Person B. So there's our free body diagram. The only thing that's changed is now the net force acting on him is not zero because he's accelerating upwards. So we're going to write tension is up, gravity is down. There's my second law expression. It's probably going to get me a point. And then we can put his mass in, 60, and the A value in that problem is 0.25. The tension is unknown, and then again, this is 588.6. So if we do 60.2 or times 0.25 plus 588.6, we're going to get the tension, and the tension is 648.85 newtons. So that is greater than that, which is why the person would accelerate up. Now, question D says, as the student is accelerating, is student A pulled up the floor? Let's go back to just this. Look at student A's weight. It's 686.7. This is 648.85. To me, it doesn't look like it's enough because the tension is not greater than his weight. What would change is actually the normal force. The normal force can drop off a bit while this is happening. So the tension's not going to be enough. And so basically the answer to problem D is no, because tension is less than the weight of person A. Right? And that's probably enough justification right then and there. You can write it out in a full sentence. You can write it like that. Either way, it makes physical sense to us. And then the last problem says, well, you know what? We want this to happen. What could this person accelerate at to actually make it happen? So that's probably the most complicated problem out of the bunch. I'm not even sure if I'm giving myself enough space here, but we'll try it out. We want the tension to be enough to get him off the floor. So what you're going to find is that, if we do use this tension and still keep up with this expression, we're going to get a smaller normal force. As he goes up the rope faster and faster and faster, and by faster I mean accelerates faster, this is going to keep dropping off. It's going to go from 98 to 50 to 25, eventually to 0. And once it hits 0, that's our threshold. That's where we cross the acceleration needed to actually lift them up. So what we're going to do is keep with this free body diagram here. So you got the normal force pointed up, you got tension pointed up, and then you got the gravity down on this person. And what we want to do is we want to set N equal to 0. That's going to get us the tension we need. Now, if we write out the expression here for sigma F, we'll still say that sigma F is 0. N, T, and gravity's down. Once you set that to 0, you find that the tension would be equal to the force of gravity here. And we already know the force of gravity is 686.7. That means that the tension must also be 686.7. we're going to stick with that, and we're going to bring that back to the first person over here, the person that's doing the climbing up the rope. That's the tension we need. We need to get above that value there so we can calculate what acceleration would be necessary for that to happen. So for person B, for that to happen, we need to solve for his acceleration. So I can write sigma F equals ma, t minus the force of gravity on person B, and the A is now unknown, but the T is 686.7, and then this is again 588.6. So if we do 686.7 minus 588.6, we get 98.1. We divide that by 60, and it turns out that this person needs an acceleration of 1.635 meters per second squared in order to get the person off the ground. And trying to do that up a rope would be quite difficult, so in my mind it's probably not going to happen, but if it were to happen, that's the acceleration he would need.